Welcome to one and all. Today we discussed about deadlock in OS. In an operating system, deadlock is one of the important concept of process management. What do you mean by deadlock? Deadlock is a situation where a set of processes are blocked because each process holding a resources and waiting for another resources occurred by some other process. See, in this example, process 1 Process 1 holding the resources 1 and waiting for resources 2. The same system, process 2 assigned to resources 2 holding the resources 2 but waiting for resources 1. See cycle to be formed. This situation is called a deadlock. So deadlock is a situation where a set of processes to be blocked for one process waiting for another one process. That is the problem. So in this chapter, we discussed about a deadlock system model, characterization, then methods for handling deadlock. The main objective of a deadlock to prevent set of concurrent process from completing their task. How to complete their task, concurrent process to be execution. The time deadlock to be occur, how to handling that. See, first system model. Each system consists of several resources. Then resources type indicated by R1, R2 up to Rm. Then resources means keyboard, printer, monitor, CPU cycles, memory space. These are called resources. Each resources has several instances. Yes, printer contain four printers available in four printers. That is called an instance of resources. A process in operating system uses resources in the following way. Yes, request the resource, use the resource. First, each process request the resource and use the resource. Then, after finishing the task, release the resource. This way to utilizing the processes. Then, what is the characterization of deadlock? Then, four conditions must hold simultaneously. First one is a mutual exclusion. That means only one process at a time use the resources. Then second one is the hold and wait. One resources hold it and waiting for another one resources. That situation is called a hold and wait. The next one is the no preemption. A resource can be released only voluntarily by the process holding it after that process has completed. One resources hold it, then waiting for another resources. After completing the process, releasing the resource. That is called no preemption. Next, circular wait means set of process running concurrently. That time one process hold sometimes and after completing the process another one process requires the resources. This way to be continuously processing. That is called circular wait. Then deadlock mutex is an important concept. See the page number 380 in your book. Next, the method resource allocation graph. What do you mean by resource allocation graph? How to allocate the resources for each process. Already assigned it and then already assigned the resources. Now, if you want to request another one edge, it's all known about this graph. So it's called a resource allocation graph. In this graph consists of vertices and edges. See, vertices indicating the process and edges indicating the resources. Then two types of edges available. One is the request edge. See, process 1 allocated to resources, then that is process 1 request to the resources, then it's called a request edge. Already that resource is assigned to process, then it is called assignment edge. Are you clear, ma? Request edge and assignment edge. Resource allocation graph is an important method for deadlock. See, in this diagram represent the process. A circle diagram represent the process. Instances, small squares is called instances. That long square is called a resources type. See, in this diagram represent the resources type with four instances. See, it's called a request edge. Process P1 request R. Then it's called a request edge. Now, resources already hold this process, then it's called a assignment edge. See, is an example of resource allocation graph. P1 request R1, that R1 already assigned to P2, then P2 request R3, that's already assigned to P3. It's an example of resource allocation graph, but sometimes cycle to be formed. See, in this diagram, P1 to R1, R1 to P2, R2, P2 to R3, R3 to P3, P3 to R2, P1. That's where to cycle form. So cycle form, then deadlock to be occur. Now, given diagram, a cycle to be formed but no deadlock because several instances consist of each resources. So when one resources consist of several instances, that time to avoid deadlock. Then this is the basic facts of deadlock. If graph contains no cycle, then no deadlock. If a graph contains cycle, only one instance of a resource, then deadlock to be occur. If several instances of resources to be had, then no possibility. Then what is the methods for handling deadlock? Then three-way: deadlock prevention, deadlock avoidance, and deadlock reduction. First, we discuss about deadlock prevention. Already we saw that four conditions. What are the conditions? Mutual exclusion, hold and wait, no preemption, circular wait. Any one of the conditions to be ensured that then it's to prevent the deadlock condition. Next one is the deadlock avoidance. Then in this deadlock avoidance, how to avoid the deadlock? Then each process declare the maximum number of resources of each type, and then how many needed, then find out how to allocate the resources. That is way dynamically examines, then it's called a deadlock avoidance algorithm, using resource allocation graph to state that a system to be ensured that then never occur a deadlock. In a resource allocation graph, you define the number of available and allocated resources and the maximum demands of the process. The system is in a safe state if there exists a sequence all process still record satisfy the currently available resources. When this condition to be satisfied, your system to be safe. Never then your system go to the unsafe state. When the system go to unsafe, that time deadlock to be occur. So now single instance of resource type, then using the method resource allocation graph, it's available. But when you consider the multiple instance of resource type, that use the Banker's algorithm. Banker's algorithm using the climb edge to convert a request edge or assignment edge. It's possible then your climb edges to be converted into request edge. Not possible then it must be prior system. See, in this way, no deadlock to be occur. But this way, your system go to the unsafe state, deadlock to be occur. So, check that system condition, request less than or equal to need, request less than or equal to available. This condition is to be satisfied, then your systems to be safe and deadlock to be avoided. This is an example of Banker's algorithm. Work out it. You can easily. Then last one is a deadlock deduction. Now your system to be enter into the deadlock state, then how to deduct that? Then using wait for graph method to deduct the algorithm. Yes, using wait for graph method to deduct the deadlock avoidance algorithm. This is the wait for graph. See, it's a resource allocation graph. Now converted into wait for graph. Which process to be waited for which process. Then you can easily detect it and remove the cycle easily. Then you recover the deadlock. See, this is the example of deadlock deduction algorithm. Work out in your class. Then deadlock recovery system. How to recover? Then terminate the process. First way, abort all deadlock process. Another one way, remove one process at a time until the deadlock cycles to be eliminated. This way to recovering the deadlock easily. Then three way to recover the deadlock: selecting a victim, rollback, and starvation concept. Thank you, girls.